This lesson is we're beginning on circular motion, uniform circular motion. We'll also be checking it out, of course. Checking out rotational quantities such as angular velocity and things like that. So while you're staring at this wonderful picture of a kitty, we will get my cat Tatiana. We will get the board set up for use. So we're beginning on chapter 6. We'll change the color to black. So recall that Newton's first law talks about what happens in the absence of external forces, that a body is at rest or constant velocity. Kind of like with kitten and catnip. Your cat will sit there and go and do nothing, and then you bring about a bunch of catnip, and then the cat goes crazy. Or string or whatever. Something like that. I know my cat likes strings and catnip. Cute, adorable thing. Jerks that stole it from me. But anyways, now, so the natural tendency of motion is to go in a straight line. In a circle, when we go into a circle, it has to be kept there by a force, which we'll talk more about that in detail later in this chapter. But really, a circle is a wonderful shape, and of course you learned all from your geometry class about definition of pi, which is circumference to its diameter, and you learned a bunch of other things about circles like secant lines, tangent lines, and things like this. You've probably learned it all from your geometry class, and I'm sure you remember every single thing that was taught. But since I'm sure you're like me and probably think, oh, I forgot it all. Don't worry, I'll remind you of what these things are. So when we're traveling in a circle, what happens is that here's your circle on an axis. This is a really bad circle, by the way. And right, so you have, of course, your velocity at different points in the circle. And you have your velocity at different points in the circle. Now, you're going about this circle, and the direction where you're going is constantly changing. This angle is constantly changing, yet I do not necessarily have to have the speed that is changing. So when we speak of uniform circular motion, this is the definition I will give to you. Okay, which is what we'll be talking about in this chapter. Uniform circular motion. Okay, so here's your definition that we're going to work with. Definition of uniform circular motion is, of course, any time That's your symbol for circle, because I'm too lazy to write the word. So okay. So it's not. So you need something to keep in mind, that the velocity is not constant in uniform circular motion. Why? Because the direction is changing. Although one aspect is being held the same, in this case the angle is changing all throughout the circle. So whether use red for this. So whether I'm at this point, this point, this point, this point, that point, all the angles for which this happens all the angles are different, and so that indicates the different direction of what's going on. So just keep that in. Uniform circular motion does not involve constant velocity, rather constant speed. And this is something very important that you need to get with the little heads. Okay. Does not involve constant velocity. We talked a little bit about that in chapter 2, but we'll talk today more in detail about what happens in this situation. Okay. The angle is constantly changing, so you have to keep that in mind when we're talking about circular motion, right? Of course, you know that when we have this circular motion, we'll talk more in detail about this in another section, where we have the forces that cause circular motion. Now, so since we're talking about circles, we're going to have to review all that stuff from geometry that you should have learned, or rather that you probably did learn and have probably forgotten by now, I'm sure. So we're going to review all of these particular points. This is a definition of uniform circular motion for you guys. What happened, basically. Now, I will make those points not. And the angle constantly changes, of course. I've clipped down those points. We're not at constant velocity, but the angle will change. It eventually repeats itself, but we'll talk more about that later. Okay. So let's add a new page. Now, to review everything you should have learned about circles, but didn't. Recall. So let's draw a nice picture of a circle. So here's our circle. Looks kind of ugly, but that's okay. Okay. Recall some definitions. We're going to recall a couple of points. We're going to recall that circumference of the circle. Circumference is, of course, the total distance around the circle. Okay. We'll use a different color for that. Let's use this blue right here, like that. So this whole length around the circle is, of course, the circumference. Circumference, which is perimeter of the circle. With circumference, we use the word circumference for that. Recall that. Okay. We also know the circle has a couple of major pieces to it. The radius. Okay, we'll use a different color for that. We'll use red. Okay, and it also has, of course, the diameter, which is twice the radius. Okay, so we know that diameter is, of course, twice the radius, and of course we know that circumference of a circle is 2 pi r, or pi times diameter, doesn't matter. Okay. Now, a very important definition which you're going to be using is the definition of a central angle. Okay, so we're going to put that down for you. And so we'll define a central angle. Is, of course, any angle formed by 2 radii. So plural for radius is radii. So any angle that's formed by the 2 radius is the central angle. So going back to my very pretty drawing up here, right above you, let's look at this point. I'm going to add another radius. Let's add a different color just to be a jerk. We'll use yellow. Alright, so it's any angle here, r. And I can, of course, define that central angle to be, we'll use letter theta for that. We'll use Greek letter theta for this. Okay? So in my picture, here, angle theta is forming the central angle. Alright. Right, so and we can call this point A, we can call this point B for just purposes of. So in this situation, so in our picture, let me get a different color. In this situation, angle theta is the central angle. Okay. So we use Greek letters to name angles in this situation. So we'll mostly be using theta. Sometimes we use phi, which looks like a little fancy F. Sometimes we'll use theta or phi, usually to name our angles. So in this case, the angle is formed by this Greek letter theta. Okay. Now, recall from your geometry classes that you learned something about the length of an arc. And you know, in a central angle, the length of the arc and, of course, the angle are exactly the same. So you'll totally recall this equation that you should have learned way back in geometry. You'll recall this. This is equal to, of course, 2 pi r divided by 360 multiplied by the number of degrees that you have. So the length of that circle. Okay. Now, where it gets to be tricky, this is the formula. The formula for arc length, in this case, S is formed by this little piece here, Let's get out a different color. Use that. In this case, S is formed by that little piece here. Now, that's the formula for the arc length, which is just a piece of the circumference, by the way. So, it's just one piece of the total length. It's just a small piece of that. That's what the arc length is. Now, what will not be so familiar to you is the unit of measurement. We will not be using degrees for this, because degrees leads us to a little bit of problems, which you can actually see in the formula here. And I'll show you more or less what happens later with this situation. So what we're going to do is take a look at this piece here. And we're going to define a new unit of measurement for us to work with. New page. So taking a look at just the piece here. Okay. 2 divided by 360 is of course 180. And since you guys are all familiar with degrees, that's oops, let me go back. Back to board 2 for a minute. Oops, I ignored the R. Oops. I wrote the R by accident. Okay. So, back to rewriting this as pi divided by 180 degrees multiplied by number of degrees. You see that the degrees cancel each other in the situation here. Alright, this degree cancels that degree. So we end up with a new unit of measurement, which we call the radian. Okay? And we'll define that for you right away here. Okay. And so the definition of a radian is the ratio arc length to its radius of the central angle. Okay. So it's the ratio of the arc length to the radius, or S divided by R, of that. So this is definition of radian. So angle theta is defined as S divided by R. This ratio is, of course, the definition of what a radian is. And this point up here is how we convert from degrees to radians. Okay? This piece up here. That's why I looked that up. So, because we're all more familiar with degrees probably than we are radians. So, to convert the two, so a conversion, it's very important, and I'll tell you why this is important shortly. In a brief second here. So to convert from degrees to radians, we multiply by, of course, pi over 180 degrees. And then, of course, to convert from radians to degrees, we multiply by 180 over pi. Okay. Now, in every single rotational equation, we're defining angles to be in radians. It is very important that you use radians for the measure of the angle. The equations do not work. You have to adjust them if you're in the degrees. They're adjusted by, of course, the factor of 100. They're adjusted by the factor of 180 over pi. But the equations that I'm going to give you now are only for the angle in radians. So this is a very important thing when we're studying circles, to keep in mind that we're using radians. We do not use degrees. We do not use degrees for these particular problems. Okay? The equations don't work otherwise. So this is a very important thing to keep in mind when we're talking about that. Okay? And so from this we derive, of course, the length of the arc, which is of course the same as its linear distance. And you're going to discover something about rotational motion, that most factors are related by its radius. So this is later here. Is, of course, the piece of the circle's circumference, or just part of it. So, of course, we use the equation S equal to r times theta for that. Okay. The arc length is a measurement of the circumference. Wow, that looks horrible. So the units for S are, of course, meters. So let's do some examples of how to find the arc length and the angle. Okay. This way I'm not just yapping my mouth giving you definitions. We'll actually do some problems that are involved. Example 1. So find the arc length of a circle with the radius of 3 meters. And theta is, of course, 270 degrees. Now, just to be a jerk, I'm going to have you convert it from degrees to radians in this situation, and just to get you in the practice of doing that. Always, when you're looking at angles or rotational motion, consider them to be, we're always doing them in radians. So they're a very important thing. So the solution for this problem is really simple. Alright, so we're going to have to convert. The first thing we want to do is convert theta So we're going to convert theta into radians. And how do we do that? By multiplying by the factor of 180 divided by pi. So it's, of course, 70 degrees multiplied by the conversion factor. We use red for that. It doesn't change. Pi divided by 180 degrees. It's 3 over 2, but just to show you the work, it's 3 over 2. At this point, you guys should know that. So simplify it. Zeros goes away. 27, 9, 3, 2. This is, of course, 3 pi divided by 2. In radians. Okay, since we didn't use the unit in calculations. Now, once we convert it, it's just a matter of using the arc length formula from this point forward. So, and of course step 2 is to use arc. Okay. S is equal to r times theta, which is of course 3 meters times 3 pi over 2 radians. And radians is something that's dimensionless, so you don't need to necessarily write it to this situation. So of course 3 times 3 is 9, so it's going to be 9 pi over 2 meters. Simple enough. So you won't have to do much of that. We're not really going to focus so much on arc length, but it's good to know just in case you're ever asked. Now, the thing I do want to talk about next is angular velocity. Now, the angle, recall that I mentioned that when we talk in a circular motion, the direction in which you're going is constantly changing. You're going at different points along the circle. In this direction, constantly changes. Okay. And so let's draw another pretty picture of a circle up here to work with. There's your pretty circle. And of course, at various points, doesn't really matter where I'm drawing it. This is theta 2, another theta 4, theta 5. Sorry, you can't see the pretty thetas there. So at every point along the circle, we have an angle, right? And so the change in angle from one point to another my colors. So this is A, B, C. And so now we're going to define another quantity, which we call angular displacement. Is of course the change in angle. Your change in angle. So the idea of a change in angle is expressed simply as delta theta. Delta theta is of course theta final minus theta initial. Okay. So so that's just expressing where you're going along the circle. So the change in your position, just like a changing in your position when you're walking around, only difference is this time you're going along the circle to do it. For example, if you're in a merry-go-round, you start at one end of the circle and you end up at a completely different end of the circle. Right? If you decide to stop it, this is what your change in angle looks like. Then, from that point, I can say that these situations are occurring in what we call time. Of course, everything involves time. So for example, let's use my pretty circle here. I'll use orange for that. So that occurs in delta t. The change in here occurs in delta t. And in here occurs your change in time. Right there is your change in time. And right here is your change in time. So 4, whatever, 1, 2, 3, 4, and 5. So all of these occur in a certain time interval. And likewise, because we measure velocity as, of course, the change in position over change in time, likewise, we have a very similar quantity in angular motion, which we call the angular velocity. Okay? Which is simply the change in angle over the change in time. So that's what we're going to define here. Okay? Angular velocity is the change in the angle over the change in time. Your book uses a fancy term, angular displacement. It's simply the change in angle over the change in time whenever it occurs. Now, we use another Greek letter, omega, for this quantity. Okay? It is one of my uber pet peeves, so do not screw this up. Okay? This is not the symbol for angular velocity. That is a W. Okay? That is a W. Get it right. Okay? This is not the symbol for angular velocity. Alright? And of course, the units for angular displacement are always radians. This is not the symbol for angular velocity, so don't have to write through omegas like this. It gets on it's one of my uber pet peeves in life. Yes, things like that do get on my nerves. So the symbol for angular velocity is this. Okay. This is a symbol for angular velocity. Why is it different? It's a big pet peeve of mine. This is the Greek letter omega, which is our symbol for angular velocity. So it is like that. Please don't mess it up by writing a simple W. You know, it looks like W, but please don't write it like that. It gets on my nerves. And one, it gets on my nerves. Two, we already have lowercase w represents something else. So we use the Greek letter omega. It does look similar to a W, but make sure you distinguish what you're doing. Okay? So our body's angular velocity is over here. Okay. We'll go to the next page. Alright, so angular velocity, it is a vector technically, so we should put vector symbols over them, but for now, it's not that big of a deal. And it's not that big of a deal for now. So the units for angular velocity are radians per second, not degrees per second, not revolutions per second, not RPMs, even though you can measure it in that. It's radians per second. Okay. It's radians per second. Right? So angular velocity tells us how fast the angle is changing in a given time, in a given time interval. Okay. Alright, so make sure you keep it like that. And of course, since in rotational motion, linear velocity is not constant, but the angular velocity is constant. Okay? So this is the point. In uniform circular motion, omega is constant. Okay. As I've said, make sure you distinguish your omegas from your w's because it is confusing for the teacher. Okay. It's not the same thing, so make sure you write your omegas all pretty and make it look nice. Okay. Now, something to keep in mind. So, something to keep in mind. See, the concept makes sense. In uniform circular motion, the angle is the angular velocity has to be constant. Why? Because you're changing the same angle in the same time throughout the motion. Okay. I would rig out my Greek sensor for you, which in the Russian style they make a full 360-degree turn of the sensor. That's really nice, actually. But hey, you know, no one's paying attention. Okay, so we'll talk more about that a little bit. Now, let's figure out how to calculate this angular velocity. Okay. Don't worry, I'm almost done yapping my mouth. So let's figure out how to calculate an angular velocity. So So to calculate the angular velocity, let's do something like that. So we're gonna we're finding the angular velocity of this figure here. So we have a circle like this. I really can't draw. Something like that. For a second. Okay. Okay, I don't know. 1, 2, 3, 4, 5. Okay. So the figure is traveling for 5 at different points along this figure here. It says 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Okay? Now, so this is our pretty figure. Now, so how do we find the solution to that? The solution, let's go to a new page. So the solution for that is clearly looking at the figure. I see I'm only traveling about a quarter of the circle. Okay, quarter of the circle. Now, since we're traveling in a quarter of a circle, I know that there are, of course, 360 degrees in a total circle, which, by the way, is 2 pi radians, just to memorize that particular idea. So, a quarter of the circle would be, well, obviously, 2 pi divided by 4. So, let's see. So we travel So we travel 1/4 of the circle. Since we're traveling 1/4 of the circle, the total is 2 pi. Divide that by 4, I get pi over 2, which is another number you might wish to memorize. We'll talk more about that in tomorrow's lecture on this particular point. Okay, we'll go over some values like that. So from this particular point, so from this particular point, it becomes that's our angle. This is our angle theta. Right. So we know our solution is to use our angular velocity is, of course, delta theta over delta t, starting from 0 and, of course, going to pi over 2. And we know we travel a total of 5 seconds. Of pi over 2 radians over 5 seconds, which is of course pi divided by 10, which you can use your fancy calculators to figure out what that is, but I will tell you what it is. It's about 0.31 seconds. Okay. 0.31 radians per second, sorry. I didn't put the radians on top. Okay. So like that. So that's how we do it. We take the angle and we divide it by the total time that it occurs in. Simply enough. Like that. So the angle is changing at 0.31 radians per second approximately. And the number, does that make sense? So it's 0.31 radians. So it's about, roughly a little more than half a radian per second is what it's changing at. Mm-hmm. Alright. Next particular point to talk about is manipulation of equations. Okay. Of course, all equations can be manipulated, and these rotational equations are no exception to that rule. So, recall this equation from recall the equation from kinematics that we worked with earlier, which is the change in position. We're going to recall this from our memory banks. Recall that recall the change in position is equal to the velocity times the change in time. Similarly, in rotation we have a very similar quantity. We have a very similar equation. It's exactly the same in its setup. We'll use red. So we have a very similar equation that's in its setup. We have this angular displacement of uniform circular motion is of course the change in angle. Okay. Now, something you ought to note, okay? Your book makes a point of mentioning the difference between angular speed and angular velocity. Well, technically there is no difference. Here's why. Because we're moving at an angle. This velocity is this movement is always occurring at an angle. So whether it's speed or its velocity, it really doesn't matter. It's always at an angle. It will always be at the angle, regardless of what you say and or do. So we really can interchange the two terms, but angular speed refers to, of course, its magnitude, but really it's kind of pushing it. And angular velocity refers to the total quantity, including the direction. But, some books will interchange the terms, and that's where I learned it, so yeah, that's all we'll do. Okay. So, yes, there is, of course, angular speed and angular velocity, but do keep in mind that while you cannot get away with this in linear terms, there's a huge difference between the two. There's not that much of a difference in angular terms. Okay? So, I'm almost done yapping my mouth. I promise. We're not done yet. So this is a similar equation. I don't want to do an example with it because you can manipulate examples. We'll do more later. We'll do more examples with this involving these equations later. I want to give you guys more of an arsenal to work with. In your car, of course, your engine measures this angular velocity by RPMs. So how does this relate to that? So in your car, you have the units RPMs. Like your engine will rev at like approximately 800 revolutions per minute RPMs. So ooh, that's an ugly M. We gotta rewrite that. Your car measures better. Your car measures your RPMs. Now, one revolution is, of course, going around the entire circle. So, one revolution is equal to 360 degrees, which is equal to 2 pi radians. So, you got it, like that. And so this is kind of the conversion between the two. Right. So let's do an example involving your RPMs, like your car, because let's face it, it's much practical. You can do an example. It's a very practical example that you'll have in your car, and if you're a total geek like me, you would totally request that your car dealer should put it in radians per second. But of course, who wants to do that? So let's do an example. So, for example, a car has a rest RPM. It's not off, of. Car has a rest RPM. Find it in find it in radians per second. Okay. And so to do that, we of course convert it. So we have 800 revolutions per minute. We want to convert it to radians per second. Because of course we know there's 60 seconds in 1 minute. There's 60 seconds in 1 minute. We divide by 60, whatever the hell. Alright, so there we go. Kiss that. Goodbye. Kiss the 0. Goodbye. 80 divided by 6. We'll leave a 3 on the bottom. And we'll leave a 40 here. To 40 revolutions per second. And of course we multiply then by the conversion factor of 2 pi. This is the 3, by the way. Do not know why my pen just decided to not cooperate with me today. Divide by 3. And 2 pi radians in 1 revolution. Kill the revolutions. 40 times 2 is 80. 80 divided by 3, just leave it alone. So it ends up being 80 pi divided by 3 radians per second. And if you want to approximate what that is, you can totally do that. You can totally figure out what that is on your calculators with your fancy adding devices. Of course, so it's 80 multiplied . It's about 83. That's approximately 83.7 radians per second. And to translate that, there's about 6.28. There is about 6.28 radians in a circle. So you're making 13 full circles per minute approximately, per second approximately. So next time, because I've yapped my mouth a little bit too much, we'll talk more about some principles such as finding and dealing with angular velocity graphs, and we'll also deal with how do we relate the quantities of linear and circular motion, which we've discussed today, we'll discuss the relationship between the quantities tomorrow in the next lecture. Now, that is all for now. I've yapped my mouth a little bit too much. We'll also talk a little bit about periods and frequencies too. And so, that is how we do that.